Welcome to video number 5. It's all about binomial expansion again, but in particular when the power is not an integer. So maybe something like a half or -1 and how to deal with that. Now actually again in your lessons you'll learn how to deal with that. It's a topic that comes up in C4, so there's nothing new here. I will go through an example very quickly in this, hopefully at 4 times the speed I write, which is always impressive if you can do that in the exam. But what I am going to look at is extensions of how this can be applied. And whilst normally in these videos I look at things that you're not likely to get asked in an exam, I did see something very similar once in a step paper. So obviously someone else has thought of this. This wasn't just me. I've also seen something more structured and quite a lot simpler, but in one of the Pearson books, which is written for Edexcel. So these problems do exist. Don't worry, I'd be very surprised if you get on a normal C4 paper. I don't think that's the case, but hopefully this will stretch some of you to understand a little bit more about what binomial expansion is about. So to start off with, I've written down the valid expansion for a binomial expansion when n isn't an integer. Obviously there's only a range of values when this is true. In this case y would have to be less than 1. Whatever the second term in here needs to be between -1 and 1, otherwise the terms don't shrink sufficiently for it to become true. And I'm going to use that expansion to expand 1 plus 8x to the power half. So again, hopefully this will go super quick, and hopefully you'll be able to see my work if I don't wiggle it around too much on the screen. Okay, here she is. 1 plus 4x minus 8x squared plus 32x cubed. And I've stated at the bottom when that expression is valid for. And actually this forms part of what I'm interested in today, the extension of this question. And actually this next bit's a question in itself. People ask me, why do we do this? And the equivalent C2 version with the integer value of n. People ask, well, what's the point? I've got a calculator. In fact, I've got my FX83 GT today. I can just type in. If I know what the value of x is, I can type in 1 plus 0.8 to the power half, and it will tell me. It can work that out. So why bother doing a long expansion when I've got this? I don't know the answer. I really don't. I can come up with excuses and look what we can demonstrate with it, but I have actually no solution anymore. Has this kind of technology made this thing redundant? Obviously it's great for your algebra, it's good practice for your maths, and it's nice to be able to do these things, but is there a purpose in real life? Hopefully someone can answer that. However, I'm going to look at this question here, which, as I said before, very unlikely to come up on your exam, but it says use the expansion of 1 plus 8x to the half, which we expanded earlier, to find an approximation for the square root of 3. Now I'm going to show you how to do this, and then I'm going to set you a challenge that's related to this. So the first thing I'm going to do is copy out my answer from the other sheet, and then I'm going to work through it and stop at some key points and explain what I'm doing. So at this point I know that there's no value for x I can substitute in to make the value inside this bracket 3. The half represents the square root, so it'd be nice if I could, but if I substituted x as 2 over 8, then it would be much too big here. I need this term to be less than 1 for this to be true, so if I try and get there straight away, I'm going to get the wrong answer. So I'm going to have to do something else. Now this step might look a little bit pointless. What I've said is that 27 over 25 can be expressed as root 9 over 25, which are both square numbers, times by root 3, which is what I want. Sorting out the square root on the 9 over 25, that gives me the 3/5 root 3. Not necessarily so important now, but there's something else that we can do with this. Okay, and this is what I can do. Root 27 over 25 is 1.08. Now, we're getting very close to this, and now you can probably see why I picked the 8 to go there. And by getting this number, which is very close to 1, and the closer to 1 we can get this, the more precise our answer is going to be, or effectively the less terms I'm going to have to do to get it to be precise. And so I've said, if I do look at 1.08, which is this, in my expansion I need x to be 0.01. And 0.01 is considerably less than an eighth, so my expansion at the top that I worked out earlier is going to be valid. So what I'm going to do now is substitute 0.01 into my expansion. And here's my final bit of work. So what I have done is I've put my bits of work in together, put in my 0.01 for my value of x in my expansion, worked that out so that 3/5 of root 3 is approximately equal to 1.0392. You might notice I only ended up using the first 3 terms. I wanted to show you that these things get quite accurate quite quickly, so 3 terms is pretty close. From this I times both sides by 5/3 to get root 3 is approximately 1.732. You may also notice I did use my calculator. I think that's sensible, and then the people I'm sure that will comment on this video will say, well, why didn't we just type root 3 into our calculator anyway? That's a question for someone who has an answer. Anyway, my challenge for you is about this piece of paper here. What I've done is I've put an assortment of surds that I'd like you to find approximations for. We've seen the root 3 approximation. I will say those of you that got the C4 at Excel Pearson book, there's an example in there that shows you how to do this one with a bit of assistance. I've written down the expansion that I used to get that one, and I've worked out the error here of my expansion using the first 3 terms. To minimise this error, all you need to do is minimise that second term in your expansion. The smaller you use here, the smallest value you use here, will give you a better approximation. So there are multiple solutions. I'll put this sheet up in our maths classroom for those of you that do come to Western College, and we'll see how much you can get filled in. Obviously, comments below. I'll fill in the sheet if you're unable to come in and fill it in for you, and let's see if we can get this filled in.